Alright, this is Calculus 1, Chapter 1, discussing functions and models. The section we'll be discussing today is 1.1, 4 ways to represent a function. So the definition of a function is a rule that assigns one element to another unique element. So the best way I can showcase this is that, let's say we are given values of a, okay, 3 values of a, and for each value that we input into a function, we are given unique values of b. So let's consider we input this first value and we get a value in b that is unique. That is still a function. Now let's consider, for example, that we input the value from the top and we input the value from the middle, and we still get the same answer in b. Is that still considered a function? The answer is yes, because for every element in domain has exactly one answer. One answer. So yes, this is still considered a function, even though we input values of a and we get the same answers in b. Right? And so to showcase that, this is still a function. Right? Okay, now let's see the flip side of that. So let's say we are given some values of a, and we are given some values of b. Now, what is not a function? Okay, let's say, for example, we input one value in a, and for that value, we are given 2 outputs from b. Is that still considered a function? No, this is considered a relation. Right? So, basically, if we go back to the definition, a function is a rule that assigns one element, right? Let's say one element of a to another unique element in b. So we assign one element from a to b. That's considered a function. But if we input a value of a and we're given 2 outputs of b, that is considered a relation. So moving on from that, the 4 ways to tell a function. I know the book, gives it, how do I say, something that, you can't really understand verbally, numerically, visually, algebraically. Basically, in layman terms, these are the 4 ways to tell a function. Form number 1 is verbally. So, they basically tell you this is a function, you're given a function, sometimes they'll give you a sentence, and, and that sentence could be, this function is, a rule that assigns one element to another unique element, something of that nature. Form number 2 is graphically. So, you're given a function, y is equal to x squared, and, simple as that, parabola, and you label your intercepts and whatnot. So that's another way to tell a function. Form number 3 is basically a chart or table. Now, how do you tell a function? Basically, from the definition, for every element that we put input from a, we are given a unique output of b. Alright, okay. So the way we tell that is, for every value of n, we input to the function, we are given a unique output. So let's say we input 0, we get 500, that's still a function. We input 1, we get 800, that's still a function. Input 2, we're given 1100, that's still a function. Alright. The 4th way is, form number 4 is by equation. So the equation can look something like P of n is equal to 500 plus, 300, and f of x is equal to, I don't know, x squared plus 1/2. That's still a function, okay? Anytime you see p of parentheses of some, letter, it's a function in layman terms, for example. So now that we got the section out of the way, let's discuss some of the problems that you might encounter on a worksheet or a quiz, for example. So say number 1, we're given f of x is equal to 1/2 x minus 4. Now this should be pretty easy. These are building off concepts that you learned in algebra, geometry, pre-calculus. So this should be pretty easy for most people. Now, what I see a lot of students fail to do is they fail to answer the whole entire question. That's why you guys keep getting a lot of -1 here and there. So let's see what we're asked. We're asked to find the domain. Okay, we're asked to find the domain, sketch graph, and label intercepts or any asymptotes, if any. So these are basically the 3 things that we need to find. So first, let's discuss the domain. What is the domain of this function? Well, x is not really limited to anything, so the domain is all real numbers. Okay. Now, basically, to sketch this graph, right? So label this as 2, 2, -2. Excuse me, 2. And -2. Right, okay, so -4. So that's our y-intercept. Okay, and 1/2. Rise over run. Okay, so we go up 1. Up 1, bing, over 2. Bam, right there. Okay, now we can just do this real quick. That's -6. So like I said, you go down 1, over 2. Oh yeah. If we could just label that, it is perfect. Just like that. Okay, so our y-intercept is basically 0, -4. Oh, 0. Oh, excuse me. This is to find the y-intercept if you want to do it algebraically instead of graphically. So f of 0 is equal to -4. This is our y-intercept, right? Now, how do we find the x-intercept? Well, basically, we plug in 0 for the function itself. So we can consider this to be y, essentially. So this would be considered y. Let me get it better. This would be considered our y. So we would plug that in. So over here to find the x-intercept, we would plug in, this is all algebraically, 0 is equal to 1/2 x minus 4, right? So if we do a little bit of algebra, 1/2 x, we multiply 2, we get 8 is equal to x, right? And so our x-intercept is simply 8, 0. Okay, so let's check mark it off. Okay, we found the domain, check. We sketched the graph, check. We found the intercepts, check. And asymptotes, if any. There's no asymptotes, so that is done. Another problem you can encounter is, g of x is equal to 2x minus 1. Okay. If we're going based off of graphs that we know, we can see that this is square root function, right? This is the how do I say, the mirror function that you should have learned in pre-calculus, since it goes something like this right here. Well, yeah, that's your typical square root function. So we're asked to find the domain of this function, and to find the domain of this particular function is that we take whatever is inside. So this would be the 2x minus 1, 2x minus 1, and we know that it must be greater than or equal to 0, right? Why is it greater than or equal to 0? Well, in order for this function to work, if we're basing it off of the mirror function, radical x, it has to be positive, right? It could be anywhere here along, so it could be quadrants 1 and 4, right? Anytime there's a negative within a square root function, then you always get an imaginary number. We don't want that. Hence the greater than or equal to 0. So we're just going to basically solve for x. 2x is greater than or equal to 1. X is greater than or equal to 1/2. Okay. Now, if we do, how do we confirm that? Well, let's say we plug in 1/2. So 2 times 1/2 minus 1. We simply get, let's see here, 1 minus 1, and we get 0, and that is just simply 0. So it works out. That's okay. Anything below 1/2, you're going to get negatives, and anytime you get a negative within a square root function, you're going to get imaginary numbers, and we don't want that. So domain is out of the way. That's taken care of. Now let's do the sketch of the graph. So if we do the basing it off the mirror function, right over here, right? The square root x, right? We know that it looks like something like this. Yeah, right? Okay. So we know that x must be greater than or equal to 1/2. Well, there you go. Right? We just plugged in x for 1/2. So let's say this is 1, and we got 0. Right? We plugged it in. So x is equal to 1/2, and we got we did all this 1/2 minus 1. And we got 0, so we know that the x-intercept is 1/2, 0. Okay, that's our x-intercept. There's no y-intercept because it doesn't intersect the y. If it intersected the y, then we'd run into some problems. So we can simply just do it from there. And there we go. Found the domain. Check. Found the x-intercept, or intercepts, excuse me. Check. And we sketch the graph. Check. That's all good. And no asymptotes. Okay. There's problem number 2. Let's consider the third problem. Let's do a rational function. So let's say p of x is equal to x plus 1. Alright. Now, the trick to all, graphing all these problems is that you need to know the basic, graphs for every function. So, like this one, it was just the basic y is equal to x plus 1. I mean, this is basic. This is basic kind of stuff. This function is just a line. Right? This function, this is our parent function, our mirror function, if you will. Alright, something like this. the parent function that you should learn in pre-calculus for this one would be something like y is equal to 1 over x, and you know that it looks something like this. Right, something like that. Can't cross the can't cross x and y. It goes to infinity. This and that. Bada bing, bada boom. Whatever. So let's discuss how we can graph this. Okay, so first off, let's do the domain, right? And we know that anytime you have a numerator, which means the top, right? Numerator over denominator, right? The denominator can't equal 0. Okay, if it equals 0, then it's it does not exist. It's undefined, essentially. So the bottom can't equal 0. So we have x minus 2 cannot equal 0. Okay, so x cannot equal 2, because if it equals 2, then we run into problems. It could equal 3, it could equal -1, it just can't equal it can't equal 2. Okay, so that's our first asymptote. So let's go ahead and graph that. Something like that, and something like that. Okay, 4 by 4. So we're gonna go by 2's here. So 2, right? So cannot pass this line, or cannot intersect that line, right? Okay. Now, do we see horizontal asymptotes? Well, basically the way to do this is that we are given, see here, if you learned from pre-calculus n and m, right? So if n is less than m, then the x-axis is the horizontal asymptote. If n equals m, then you have to do y is equal to a over b. And then, what was the last one? N is greater than m. And I think this is, oh yeah, no horizontal asymptote, but you have a slant, diagonal, or oblique asymptote, right? So, A, B. Okay, we could clearly see that n and m are 1. So they equal each other. So the way to do that is that we do y, right, per the definition, right over here. Y is equal to a over b. The number in front of x is 1. And b, right here, the number in front of x is 1. So y is equal to 1. That's our horizontal asymptote. So let's go ahead and do that right there. So we got 2 there. So y would look something like that. Y is equal to 1, right? Okay, now if we're looking at the parent function, see, right? We look at something like that, then obviously we know that it's going to look something like this. Let me go and erase this part right here. Alright, it's going to look something like this. So as x gets bigger and bigger and bigger, this this line is going to get closer and closer to y is equal to 1. So this is going to get closer and closer to y is equal to 1 as the y values get bigger and bigger. This line right here is going to get closer to x is equal to 2, right? Okay. Now we know that same thing here. Actually, before we even graph that, we need to define the x-intercepts. So the best way to find the x-intercept and the y-intercept is basically just to plug in some values for these equations. So the best way to do it is basically just plug in a simple value of, let's say, I don't know, let's say we plug in -1 for x, right? So p of -1 is equal to -1 plus 1, right? All over, -1 minus 2, so that's 0. 0 over -3, and that's just 0. So there we go. We found our first x-intercept. First x-intercept is -1, 0. Right? Okay, so let's say we plug in, I don't know. See, we want to try to find whole numbers, because if we plug in value that gives us fractions, it's going to be hard to graph that. So you want to think this kind of algebraically and find whole numbers, if you will. So looking at this, let's say we plug in, I don't know, for y, let's say we plug in -1/2. Let's do -1/2. So this is our x-intercept over here. To find our y-intercept, like before. Okay, we plug in -1/2 is equal to x plus 1 over x minus 2. Yeah, so the best way to do this is to x minus 2 is equal to x plus 1, right? So we get -1/2 x plus 1 is equal to x plus 1, right? Okay, we get, let's see here, let's say, -3/2 x is equal to 0, right? So x is equal to 0. There we go. Easy. So our y-intercept is -1/2, comma, oh, excuse me, 0, comma, -1/2. How do I find that? Well, you kind of have to think about it and say to yourself, how can I get, what value of y will give me 0 for x? And that might not be the best way to describe it, but that's the way I do it. And you just kind of have to think about it and say to yourself, okay, what value is going to intercept the y-axis? So let's see here. -1 is like right about here. So excuse me, -1 is right about there. So we're going to plug in the y-intercept right there. And we'll graph that. So this is getting closer and closer, right? But it expands out, and it goes down, 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 get closer, closer, closer. But never touches. That's the key. Never touches that. All right, there we go. So found the domain. Check. Found the y-intercept, or excuse me. So we found the domain. We found the asymptotes. So to find the asymptote is basically the vertical asymptote would be x cannot equal 2, right there. We found the y, the horizontal asymptote per the rules. Remember, n over m. Right. So we discussed that, and we found that the horizontal asymptote is 1. Right there. From there, we use the parent function right over here, and we graph the general graph, and then from there we found the X and Y intercepts. We found the x-intercept by simply plugging in a value algebraically, because I thought about what can I do to get a value of 0, what input can I plug in to get a value of 0. That's the way you want to think about it, algebraically. Same thing here for the y-intercept, and there we go. That's how you get it done. Okay, let's do another one. Let's do a trying to think of something here. Piecewise function. Those are always fun. So for, let's say we're given f of x is equal to x when x is less than 2, and 3x when x is greater than or equal to 2. So the best way to graph a piecewise function is that you want to consider the values on which you're restricted for that particular function. Excuse me. So for example, f of x is equal to x when x is less than 2, right? So let's go ahead and get this started. Let's see here. Trying to do this without messing up. So something like that. Okay. So let's say x is less than 2. So we first we need to consider the graph of x. So what would x look like? For we plug in 0, we're gonna get 0. We plug in 1, we're gonna get 1. We plug in 2, we're gonna get 2. So it would be considered right here. And like I said, you plug in 1, you get 1. You plug in 0, you get 0. You plug in -1, you're gonna get -1. And so on and so forth. It's gonna look something like this. Basically until infinity. Right. Now let's consider 3x. Right. So let's say we plug in a value of 2 for 3x. Right. So f of x is equal to 3x whenever x is greater than or equal to 2. So let's say we plug in 2. We get 6. Right. So our point is 2, 6. That's our beginning point, right? So we go to 2 over 1, 2, and then up 6. So 3, 4. Oh, this is going to be kind of a little tough here. For the sake of graphing this, let's just say this is 3, 4, 5, 6, right? Plug in there. That's our beginning point, and we know it goes up to infinity. And we can graph it something like that. Booyah. There we go. So we don't need to say the domain, because the domain is already given. The x-intercept. Do we even have an intercept? Yeah, we have 0, 0. Right. No y-intercepts. No asymptotes, so we're done. Moving on. Let's see here. Sometimes I know that some quizzes and tests, they like to throw some pre-calculus, reviews at you. So sometimes, determine whether the function is even, odd, or neither. So even, odd, or neither, right? So let me give you an example of how to do that. So let's say we're given a function of f of x is equal to 1 over x to the 4th. Basically, how you tell whether it's even, odd, or neither is that if we plug in f of negative x to the function and we do some algebra, do a little bit of work. If it comes out negative, it's obviously odd. If it comes out even, then it's obviously even. So let's just basically showcase that. So negative x to the 4th, and that is simply just 1 over x to the 4th. So that is even. Okay, and so on and so forth. And until this is just basically pre-calculus stuff that sometimes your calculus teacher will throw a whammy at you. Okay, let's continue. Let's say we're given a function g of x is equal to x squared plus 1, right? These are all reviewed questions, by the way. These are all questions that your teacher may or may not give you. So I'm trying to cover what teachers typically like to give on quizzes or worksheets or tests, for example. So let's say, I don't know, the basic, let's find g of 0. Say that's number g of 0, g of negative 2, and g of a. All right. So this is easy. You plug in values of 0 in place of x, right? So g of 0, we do 0 squared plus 1, and we get 1. So therefore, g of 0 is equal to 1, right? Basically, whatever's inside the parentheses is telling you to place that in place of x for the function right up here. So start with the next one, g of negative 2. So like I said, you place in negative 2 in place of x. So negative 2 squared plus 1. Okay, that's simply just 4 plus 1, which is equal to 5. So, therefore, g of negative 2 is equal to 5. Right? Let's say g of a. Same thing, you place a in place of x. So a squared plus 1 is equal to a squared plus 1. Therefore, g of a is equal to a squared plus 1. There, simple. Another question that you may or may not get is the difference quotient. Okay, you're asked to evaluate the difference quotient. Let's say g of 4 plus h minus g of 4 all over h, right? This is the difference quotient that you learn in pre-calculus. So, same thing, we're given the same function of g of x is equal to x squared plus 1. To solve this, basically what we learned up here. So these 3 problems, right? So we're given g of 4 plus h. Okay, you want to plug that in place of x for the function right here, right? So let's go ahead and do that first. Okay, we're doing it step by step. 4 plus h. So that's simply just 4 plus h squared plus 1, right? Do a little bit of algebra here. We are going to get 16 plus 8h plus h squared plus 1. And we are simply going to get h squared plus 8h plus 17. Okay, the next one we are given g of 4. So we are given 4 squared plus 1, we get 17. Right, so we have our substitutes, for example. So this would be g of 4 plus h is equal to h squared plus 8h plus 17. And we're given g of 4 is equal to 17. So we go ahead and place these substitutes in the difference quotient, right? So let's go ahead and do that. So we are given write it out, 4 plus h minus g of 4 all over h. Plug those in, we get h squared plus 8h plus 17 minus 17 all over h, right? So the 17's cancel. All you're left with is h squared plus 8h all over h. We could factor out an h plus 8 all over h. The h's cancel. All we are left with is h plus 8. There you go. Evaluated, done deal. Okay, you get 100%. credit, bingo. Another one is simply what we just discussed. Plot the graph. Plot the graph. Label intercepts, and state domain for the function, right? Yeah. So g of x is equal to x squared plus 1. Okay, there's nothing restricting, to a point where we're going to get imaginary numbers or otherwise, and it wouldn't make any sense. So the domain is simply just all real numbers. Plotting the graph, like I said, the parent function of x squared is basically an asymptote. Right, so the parent function is y is equal to x squared, and it's simply just a parabola, something like that. Right, the only difference now is that we got an x plus 1, so we just move up 1, right, and something like that. Label intercept, so the only intercept we have is the y-intercept, so 0, 1. That is our y-intercept, 0, 1. Bam, done deal. Another, sketch graph you might have. This one, let's see here, what is one I haven't done? We can do the absolute value. We can do that one. Absolute value is like the x squared, right? It's like a parabola, but it's like a V-shape. Like it's strictly V-shaped. So the way we could do this is simply, look at the parent function. Like I said, the absolute value of x, simply just, like I said, a V. It's like a parabola, but just with straight lines. Something like that. So, from what we learned in pre-calc, we go left 2, down 1, okay? Like I said, you want to start with the parent function. Of the graph, so 0, 0, 1, 1, negative 1, 1, right? So let's say this is our mirror image that we start from. And we are asked to go left 2, 1, 2, down 1, left 2, 1, 2, down 1, left 2, 1, 2, down 1. And this is what we are left with. Right there. Okay, basically our x-intercepts is -3, 0, and -1, 0. Y-intercept, basically on the graph, what we have is 0, 1. So there we go. That would be our graph. So, hope you enjoyed, hope you learned a lot, and hope you will do well. Thanks for watching.